Welcome to section 7.2. This section covers volume, and it's split into two very different, distinct parts. The first part that we're going to start today involves volumes of revolution. We're going to take an existing region, and you'll see a bunch of them, they're colored in yellow, and we're going to start whirling them around an axis of revolution. And as we rotate these things, they're going to carve out 3D volumes. And there are two methods for finding volumes of revolution, the disk method and the washer method. We'll spend probably 3 days on doing disk and washer method problems. This is pretty intense. And then after that, we're going to finish section 7.2, still using volumes, but instead of revolving things, they'll be already 3D shapes. And we're going to cut them up. We're going to slice and dice them and look at their cross sections. So 7.2 is split into a couple different sections, like I mentioned, even though they're both in 7.2. So, okay, without further ado, disk method and washer method. Here are the formulas that you're going to need to know. This will make a lot more sense when we start to see examples, but one thing about the disk method is that a disk is really just a circle. And when you think about, hey, what's the area of a circle? It's pi r squared. And you can see the pi r squared right in the formula. I kick the pi out, and that's usually what the book will do because, pi is a number, it's 3.14. And there's the r squared, radius squared. Okay, when you integrate something that's squared, it becomes cubic, and therefore it becomes three-dimensional, and you end up with volume. All right, the washer method is the same thing as the disk method. It's pi r squared if you do some distributive, where the large uppercase R is the outer radius, and little r is the donut hole, if you will, or the inner radius. I found a couple videos on YouTube that do a nice job with animations. This is really tough stuff to draw on a flat surface because it is three-dimensional, so believe it or not, and here in class we're going to watch a couple of YouTube videos. As you can see, we're taking the equation, which is a square root equation, we're revolving it around the x-axis, and it creates a 3D shape. If we just grab one slice out of this shape and pull it out and inspect it, you can see that that's a circle. And there's a bunch of different circles. Some are larger, some are smaller. But if you add up all those tiny little skinny circles together, which is what integration is, you'll get the volume of the shape. So that's why the pi r squared gets integrated. Here's another example. This time we're going to go around the y-axis. You can see there's a 3D shape. It looks a little bit like a funnel, except that there's no bottom opening. And again, every little cross section there is round. It's a circle. All these little pieces of circles are adding up to make that 3D shape as you whip this thing around the y-axis. So pi radius squared. Hopefully that kind of helps out a little bit. I hope those videos helped. My guess is they're probably going to show up a little bit off-center once I edit this, but that's going to be the best I can do here, given the circumstances. So let's look at some of the problems that I made up, starting with my number 1. Okay, it says find the volume of the solid generated by revolving the region bounded by y equals negative 1/2 x plus 4, that's a line, and the curves, I call them curves to be generic, but really x equals 0 and y equals 0 are just the coordinate axes. So that's going to be a region in quadrant 1. It's going to look like a triangle, and we're going to take this triangle around the x-axis. A picture's worth 1,000 words, but when you're doing volumes of revolution, a picture's worth like 10,000 words. So I'm going to make a drawing of this region first. There we go. So you can see the line y equals negative 1/2 x plus 4. It's sloping downward. And it's going to hit the points 0, 4, and 8, 0. Now we're going to take this and we're going to go around the x-axis. So imagine this thing starting to rotate or revolve around the x-axis. Like you're in a factory and somebody hits a big button on the wall, boom, and this thing starts to go around. Zoom, 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 zoom. And it picks up speed and starts to go super fast, and you can see that it will cut out a three-dimensional shape. It's going to superimpose itself on the other side of the x-axis. And what I like to do is I like to make what I call a representative rectangle. I just pick a generic blue rectangular strip and I draw it into the picture. I purposely didn't draw it right up the middle because I don't want people thinking it's halfway. It's totally a random location. I don't know how far over this is, so I just call it x. And so therefore, if this is x, this point is going to be the point x comma 0 on the x-axis. And this point, like every other point on a flat surface, is x comma y. X comma y. Of course, I'm not writing a letter y, as you noticed. I wrote negative 1/2 x plus 4 because if you're on the line, you have to obey the equation of the line. That keeps extra variables out of my work. Okay, fantastic. All right, so if this goes around the x-axis, you can see that you're going to form a circular disc. This thing's going to whirl around and become basically like a frisbee. And the radius of the frisbee is simply top minus bottom, which in this case would be the negative 1/2 x plus 4 minus the 0. So the radius is negative 1/2 x plus 4. You're going to have other rectangles like this green one, the larger red one, and some even smaller ones to the right that are also going to be revolving around the x-axis, forming circles of their own. And all these different multicolored circles together will make the 3D shape. The volume of this shape can be obtained by using disk method. The reason this is disk method instead of washer is because every single rectangle, the red one, the green one, the blue one, all these black rectangles I'm making now, every single one of them physically touch the axis of revolution, the x-axis. Every single one hits and makes contact with the x-axis. Every single one of them. Therefore, there are no holes or gaps. The moment one of them misses the x-axis and you have a hole or a gap, then you need washer method. All right, so this is going to be disk. We only need one radius, and we have it already. So the formula is pi r squared, integrated. I'm going to kick the pi out. We're going to integrate from 0 to 8. And those are the limits along the x-axis, so we have a dx at the end. We also have x's in our work because it's pi radius squared. But remember, the radius we know. It's right up here, so we'll just drag it and put it in. Now I have to prepare you for the AP exam, and I don't know if this is going to be a calculator problem or a non-calculator problem. I have seen volumes of revolution in both sections, so I'm going to take the first two problems, and I'm going to do them without a calculator. And then for the rest of this, I'll use a calculator so it doesn't get too long and boring, to be honest. All right, so I'm going to FOIL this out. All right, since I feel like I'm going to start running out of room, I'm going to go to a blank sheet of paper, recopy this, and finish it, and then I'll bring my answer back. Excellent. So as I integrate, the pi is still out there. 1/4 x squared is going to become 1/12 x to the third, and then we'll have minus 2x squared plus 16x, going from 0 to 8. All right, plugging the 8 in, we're going to end up with 8 cubed, which is 512. There's a 1/12 on that. We'll put the 8 into here. 8 times 8, that's 64 times negative 2, that's going to be minus 128. However, 16 times 8 is positive 128. So they're just going to cancel out. And so I have 512 over 12. Those are both even numbers. So I'll be able to cancel them just by dividing by 2. Get 256 pi over 6. Oop, you know what? I could have divided by 4. All right, let's get greedy. Cut it in half again. Half of 256 will be 128. And the volume of revolution is going to be 128 pi over 3 cubic units. All right, our very first disk method problem, volumes of revolution. You don't have to say cubic units, by the way. I just think it's a fantastic habit. If it's cubic feet or cubic miles or cubic anything else that they give you, you have to say it. So why not get in that good habit? You know, while we're at it, I just thought of something here. When this shape goes around the x-axis and revolves and makes a 3D shape, you know what that shape's going to look like? It's going to be a cone. And it just hit me that we know what the volume of a cone is from geometry. The formula for volume of a cone is 1/3 pi r squared h. And if you don't know that, don't sweat the details. I'm not going to have you memorize that. You will have to know all the formulas for two-dimensional shapes. Anything that's 3D, like cones or cylinders or spheres, we'll give you those formulas. If it happens to be a pyramid for some reason, we'll provide you with volume and surface area formulas. So will College Board. All right, but if you look at this cone, it's on its side, so this is actually the height here, and the radius would be this. And you remember it's rotating, so it's going to make a circular base. The volume of this cone is 1/3 pi. I'm just going to write pi over 3 to save some space. Radius squared, well, the radius is 4, so if you square that, that's 16. And the height is 8. And 16 times 8 happens to be 128, and my gosh, look at that. It matches the calculus, which is good because I've taught geometry and calc both, and I don't want to be a liar, so both of them do work. All right, fantastic. As you can see, the geometry formula was much easier, which probably leads people to ask, why don't we just use geometry then? Why do we have to integrate? And that's a great question, which is why I invented number 2. Because with y equals 1/2 x squared, which is a bit of a parabola, you're not going to be able to use geometry formulas when you rotate this around the x-axis. Here it is, and I've also included the vertical lines x equals 3 and x equals 6 as part of my boundaries. Y equals 0 is the x-axis. And we're going to revolve this around the x-axis. We're going to go about the x-axis. So this thing's going to go around like so. It's going to superimpose on the other side of the x-axis. And people are like, oh, it looks like a sideways volcano. Or other people are like, oh, it looks like one of those wide-brimmed hats you would wear in the field so you keep the sun off your face. Well, geometry doesn't have a formula for a volcano, so it's not going to be a cone. So you have to use calculus now. All right, so I'm going to make a little representative rectangle for myself. I find that the people who take 5 seconds per problem and make this representative rectangle usually score about 1 letter grade higher than the people that don't do this. This is a great, great, great strategy to use. I would highly recommend doing this. All right. That blue representative rectangle also flips around the x-axis, superimposing on the other side, making a disk. Its radius will simply be this distance right here, which again is top minus bottom. So it's going to be 1/2 x squared for the radius. Again, every single representative rectangle that we would make in the yellow region hits the x-axis. There's no holes, there's no gaps. So this is also a disk method problem. We haven't seen washer yet. Don't worry, we will. We're only integrating from x equals 3 to x equals 6. So 3 and 6 become the limits of integration. So it's pi radius squared. And it's dx because we're hitting the x-axis with all these rectangles. And the radius, as I mentioned, is the 1/2 x squared. So it's 1/2 x squared getting squared, which will be 1/4 x to the 4th. I'm going to kick the 1/4 out, though. The 1/4 went out and joined the pi. The x to the 4th that's left will integrate into 1/5 x to the 5th. I'm also going to take the 1/5 and kick it out as well. That's going to make a pi over 20 out front. Now, of course, if you have a calculator, by all means, use the calculator. If you don't, you just have to figure out, hey, what's 6 to the 5th and what's 3 to the 5th? And they're going to have some very large numbers, needless to say. 6 to the 5th is 7776. $7,776. I don't know if I'm proud or embarrassed that I know that, but I happen to know that. I'm a math teacher, so hey. 3 to the 5th is 243. Remember, it's minus in between. We're doing first fundamental theorem, so you have to subtract. And when you do subtract these, you're going to get 7533, 7,533. And so let's just wrap this up and make this a final answer. 7,533 pi over 20 cubic units. And that would be the volume of that hat or volcano or whatever it is. All right, that's it for day number 1 of disk and washer methods. We've got a couple more days. We're really going to spread this out because this is tedious and it takes time to do a good job. And I want you to stay neat and I don't want you to be overwhelmed. So, I'll see you later.